So section 7.7 is kind of an interesting add-on to this course, and it's a nice practical one. It actually gets to things that are close to what I did as a graduate student, studying numerical analysis, and that's basically implementing these kinds of things on a computer or a calculator, stuff like that. Now, there's a lot of functions for which we just simply can't find an antiderivative. An example would be the integral of e to the x squared dx. Another one might be the integral of tangent of x cubed dx. I don't know, maybe there's something obscure for that one, but I don't think there is for this one. And it becomes a problem to try and find some answers to these questions. If I wanted to find an integral, say, between 0 and pi over 4, or 0 and 100, what do? Well, there's a couple different approaches. One of them is called the trapezoid rule, and the other one is called Simpson's rule. Now, the trapezoid rule gets its name from, exactly what you would think it's coming from. What we're going to do to try and approximate an area is, instead of using a bunch of rectangles, which is what we've done before, we did rectangles with, the left-hand endpoint. You can do them with the right-hand endpoint, or you can do it with the middle endpoint, or the middle point. Instead of doing that, how about if we do something a little bit more efficient, a little bit better approximation, and that would be a trapezoid. So we can fill in trapezoids in here. Now, what do you think? Which one looks like a better approximation? The rectangles or the trapezoids? Yeah, trapezoids look like a much better approximation. So if you add more rectangle or add more intervals, then this approximation is just going to get better and better and better. In fact, if you move on down a little bit, you can see what happens to the error in this method. It's going to decrease and decrease and decrease. So eventually you get a really good approximation with a little, n equals 25 is a relatively small number of intervals, especially if you're running this on a computer. So people have industrialized this formula. They've analyzed it and said, you know what? If we wanted to find this, then we can approximate it this way. So you're going to take delta x, that's going to be the length of our interval. So that's your delta x right here, is the length of the interval divided by n, length of the interval. I take that and divide it by the number of intervals. Now when I say length of the interval, it's length of the interval that you're integrating over divided by the number of subintervals. So that's what this is all about, your delta x. Divide your delta x by 2, and then you're going to multiply it by this strange sum. Basically, it's what would happen if you try to do this repeatedly with a bunch of adjacent intervals, and you get this weird sum that looks like this. Now the important part to notice is that you're going to be evaluating the function at all these points, but other than the endpoints, x sub 0, that's your a, x sub n, that's your b. Other than the endpoints, all these other points get multiplied by 2. That is, the function gets multiplied by 2 when you evaluate those. So, okay, let's see how that looks. We're going to apply that to example A here. Where we've got the sine of x, sine of the square root of x between 3 and 6. We want 6 subintervals here. Now, I didn't go through and change up my graph. Let's see here. Let's just make a change here. Let's just make that a 0. That way it matches the graph. We're going to try and find this integral, at least approximately, using the trapezoid rule. So by doing this, we're going to get a little bit more friendly points. Let's see what happens here. Example A. Integral from 0 to 6 sine of the square root of x dx n equals 6 subintervals. All right, so let's keep track of some of our points here. 0, 1, 2, 3, 4, 5, and 6. So there's really 7 endpoints that contain this interval. That's okay. There's still 6 subintervals. We'll start by calculating delta x. Delta x is going to be 6 minus 0 divided by 6, and that's going to be a 1. If I plug that into my little formula here, it'll be delta x over 2 times f of 0 plus 2 times f of 1 plus 2 times f of 2 plus 2 times f of 3, and I'm sorry to do this to you, 2 times f of 4, 2 times f of 5. But when it gets to the endpoint of that last subinterval, it's just going to be f of 6. Let's fill in some information here. Delta x was 1 over 2. Our function, I was calling this f of 0, f of 1, etc. Our function is this part right here. That is your f of x. So let's see. If I plugged in the 0, I'd have the sine of 0 plus 2 times the sine of 1 plus 2 times the sine of 2. And this gets a little bit monotonous, which is why we usually do this on a computer or at the very least a graphing calculator. 2 times the sine of 4, 2 times the sine of 5 plus the sine of 6. I actually square root of that. Square root, square root, square root, square root, and square root. So we got a lot of calculator work to do ahead of us. It's not fun. Trying to think if there's a clever way we can do this. There is, but it might be a little bit too cutesy and clever. So we'll just do it brute force. Now, does anyone know what the sine of 0 is? Yeah, it's 0. So let's just skip that one. We'll end up with 2 times the sine of square root of 1 is just 1. 2 times the sine of square root of 2 plus 2 times sine of the square root of 3 plus 2 times sine of 2, 2 times sine of the square root of 6 or square root of 5, and sine of the square root of 6. If you did want to be clever, we could add up these and factor out the 2. Might be a little bit easier. But let's just go through and bang this one out. kind of want to be cutesy and clever with some of this stuff, but I don't want to overwhelm you with it either. So 2 times the sine of 1 plus 2 times the sine of the square root of 2. Let's make sure we put a right parenthesis there, and so on. 2 times the sine of the square root of 3. I think I'm going to make a mental note to choose n equal 4 subintervals next time I do this one. Plus 2 times. Oh, I did the sine inverse. Thank you. Yeah. All right. Thank you. 2 times sine of the square root. Well, I don't need it. I just put a 2 there. Plus 2 times sine of the square root of 5. Plus, finally, sine of the square root of 6. And I had 2 parentheses, one to close off the sine, one to close off that whole big thing. And bam. Let's see what I get. All right, well, how good was that? How good is it compared to what Texas Instruments gave us? One thing you want to make sure of is that you're in radian mode before you run this calculation. Let's see about what Texas Instrument will give us. So Math 9, 0 to 6. One more time, 0 to 6. Sine of the square root of x dx. Not so great. I mean, not bad. But then again, we only use 6 subintervals. So, you know, overall it wasn't too bad. In fact, what you could do is you could take and kind of compare these two numbers. This one divided by our previous answer, second and then answer key, times by 100%. We were within 5%. Now, so it wasn't great, but it wasn't horrible. Okay, but it's just an example of using what's called the trapezoid rule. Now, perhaps a better place where you'd use the trapezoid rule is if you actually had numerical data, such as the case on the back side of our handout. So let's take a look at that. So this is, again, a place where you could use some numerical integration. In fact, we don't have a function for this at all, so you could actually just say, all right, well, let's figure it out with the trapezoid rule, or we'll go back and do both of these with Simpson's rule. Simpson's rule is a different way to approximate things. It's actually really good for as basic as it is. It's a really good method by which you can approximate things. So let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8 intervals. Now, of course, you need 9 points to contain those 8 intervals. But in our case, n equals 8. Let's see if we can't figure out a few things about this. So n equals 8. We're going to work on the interval from 0 to 40. So let's figure out what delta x is. Delta x is going to be 40 minus 0 over 8 intervals. That's going to give us 5. So that's how wide each of our subintervals is going to be. We're going to keep our subintervals the same width, at least for this exercise. Okay, let's see about finding the actual approximate area underneath this curve using Simpson's rule. I mean, not Simpson's rule, the trapezoid rule. So it's going to be delta x over 2 times f of 0. Remember, at the endpoints, you don't have that 2. But at every other place, 2 times f of 5 plus 2 times f of 10. And I'm not going to go through all this like I did the last one because we have a little bit more work to do. It's going to end up as 2 times f of 30 plus 2 times f of 35. And finally, plus f of 40. Delta x was 5, so this is going to become 5 over 2. What's f of 0? Can anyone tell me what f of 0 is? Yeah, 68. That's coming from down here, in case you're wondering. So at f of 5, heart rate had jumped up to 149, so 2 times 149, and so on. Your numbers here for f of 5, f of 10, etc. are all going to be coming from this down here. So 2 times 150 plus 2 times 156. 2 times 156 again. 2 times 157. 2 times 166. Plus 2 times 162. And last but not least, 153. Does that 153 get multiplied by 2? It does not. So a lot of grunt work to do here. I'm curious. Would this be an easy problem or a hard problem to put on an exam for something like this?
Easy.
Easy? Okay. All right. Just curious. Let's add all this stuff up, and then I'll multiply by the 5/2 as a final step. I don't think there's any nice shortcuts you can do here other than if you wanted to add these two up and then add up all these numbers and then finally multiply it by 2. I don't know. Feels like a little bit more work than it's worth. So I'll start with 68 plus 2 times 149 plus 2 times 150 plus 2 times, times 156 plus 2 times 156 again plus 2 times 157 plus 2 times 166 plus 2 times 162 plus 153. So if I did put it on an exam, what I'd probably appreciate is something like this, that's equal to 5/2 times, what was the number that I had there? 2,413. So multiply that number by 2.5. 6,032.5. Yay. Nothing too dramatic there, but it's kind of cool. The total area underneath here represents how many times this person's heart beat during exercise or whatever sport was going on here. Probably biking. You can tell where they hit the hill, right? Heart rate jumped up to 166. So that's the trapezoid rule. Simpson's rule is a little bit more sophisticated. I don't really know anything about Simpson to tell you historically. I apologize about that. Let's back this down a little bit. Let's go down to 2 n equals 2. Well, even n equals 1 might be even work. So obviously, if the trapezoid rule was approximating things with one interval, it'd probably be a bad approximation. But we can also do things with Simpson's rule. And let me choose Simpson's rule. Without describing anything, does Simpson's rule look like it's a better approximation? What you're doing with Simpson's rule is you're fitting a parabola to 3 points on this graph. So once you fit that, then you run a parabola through it, and yeah, you can get a pretty good approximation very quickly. Let's let n equal 2. Now you're fitting 2 parabolas. That looks even better. Let's take a look at our error. Our error is, less than 2% at this point. That's really good. Comparing the error to the exact value, yeah, we're within 2%. That's just with n equal 2. If we zoom this up, our error just really gets very, very small. And look at how many zeros there are in our error term. Now, just like our trapezoid rule, we can industrialize this and say, all right, well, let's just come up with a rule to apply this to a repeated amount of intervals. So that rule is going to look a lot like the trapezoid rule. We're just going to have different coefficients here. So the coefficients have a different pattern. That pattern for the coefficients is 1, 4, 2, 4, 2, etc., all the way down to 2, 4, 1. So it keeps on repeating itself all the way until you get to the end. Like the trapezoid rule, at the end, you're just going to evaluate the function. You're not going to evaluate 2 times the function or 4 times the function. It's just going to be the function. Now I'll give you your choice. We can either apply Simpson's rule to this one here or this one here. Which one would you rather? First one or the second one? Second one? All right. Let's apply Simpson's rule to this one. Apply Simpson's rule. Let's see here. Okay, so one other thing that's going to change from the trapezoid rule versus Simpson's rule is that you're going to divide by 3 instead of divide by 2 out in front. Your delta x is still going to be the same. It's going to be x. Delta x is b minus a over n. Our n in this case is still the same 8 that it was. So let's run through this.
How did you find n again?
N is going to be given to you. Thank you.
Okay.
N will be given to you. It's not something that you're supposed to just inherently know. N represents the number of intervals, or the subintervals. N equals the number of subintervals. B minus A is the length of the entire interval. So for Simpson's rule, let's start by calculating delta x again. Delta x is going to be our b minus a over n, which is going to be 40 minus 0 over 8. So we'll still end up with 5 like we did the previous one. I mean, nothing much has changed in that regard. But Simpson's rule looks a little bit different. I'm going to take my delta x and divide it by 3. I'm going to start out with f of 0. And then I got to execute that pattern. And let me try and highlight that pattern this way. It's going to be 4 times f of 5 plus 2 times f of 10 plus 4 times f of 15, and so on. This pattern is going to keep on alternating until we get to the next to last one. If you want a fancy word to impress your friends with, that would be penultimate, be the next to last, plus 4 times f of 25, 2 times f of 30, four times f of 35, and f of 40. So keep in mind that that pattern goes to the next to the last, doesn't include the first either. So pretty much we're going to be repeating our calculation from just a minute ago. It's just now that we've got 4s and 2s as opposed to a bunch of 2s. All right. Let's clear this out. Actually, I think I will do one more step here. So it's going to be 5/3. F of 0 was going to be 68 plus 4 times 149 plus 2 times 150 plus 4 times 156 plus 2 times 156 plus 4 times 166 plus 2 times 35 plus not 2 times 35. How about 162. Something I must have skipped something. 2 times 156. Oh, I skipped the 157. There we go. So it'd be 4 times 157 2 times 156 or 166, and then 4 times 162, and finally 153. Okay, let's bang this one out. So let's see here. I'm just going to do the inner part first. So 68 plus 4 times 149 plus 2 times 150. Could have put 300 in, I guess. Plus 4 times 156 plus 2 times 156 plus 4 times 157 plus 2 times 166 plus 4 times 162 plus 153 times by 5 divided by 3. So 6101 and 2/3. Let's see, so 5/3 times 3661 6106 and 2/3. I think I fit a polynomial to this one to try and see just how good either one of these was. So let's take a look at that. Let's see, down here. So let's see the area underneath this curve, at least according to that polynomial. And it's a numerical integration. So 6,086.895. That's not too bad. That looks pretty close to my 6106. Not sure which one was actually more correct because we don't have the data in between, but this one looks pretty reasonable. I'd probably, if I was going to go back, I'd probably fit a tighter polynomial to this. But in any case, looking good either way. Comments or thoughts on Simpson's rule? Are you good with Simpson's rule, trapezoid rule? Pretty straightforward, I hope. Do you want to go back and apply Simpson's rule to the sine function here? Yes, no, maybe so?
Yeah.
I got a yes? Oh boy. We're going to get you an escort out of class to your car. All right, let's do it. I'm kind of curious to see how Simpson's rule would do versus the trapezoid rule here. So, my apologies. One last one. Don't worry, I'll have public safety here in time for you. All right. Okay. So going back to example A with trapezoid or Simpson's rule this time, we still have the same delta x as before. Delta x is going to be 6 minus 0 over 6, which is 1. So out in front, I'm going to have delta x over 3, so 1 over 3 times sine of the square root of 0 plus 4 times the sine of the square root of 1 plus 2 times the sine of the square root of 2. And I guess I didn't need a square root there. I didn't write one there. 2 times the sine of the square root of 2 plus 4 times the sine of the square root of 3 plus 2 times the sine of the square root of 4, which is just 2. So let's make our life a little bit easier there. 4 times the sine of the square root of 5. And last but not least, sine of the square root of 6. So again, a lot of grunt work to do. Probably if I had you do this on a test, what I would like is that total in the middle, and then we'll divide it by 3. So let's set about getting these things. In fact, we can start out by making our life easier by noticing that's just a 0. So that'll make that a little easier. Clear out a lot of junk here. I want 4 times the sine of 1 plus 2 times the sine of the square root of 2 plus 4 times the sine of the square root of 3 plus 2 times sine of the square root of, actually just 2, right? I'm going to get rid of, we'll just make that a 2. Plus 4 times the sine of the square root of 5. Right parenthesis there. Plus the sine of the square root of 6. Square root of 6. And close that all off. Actually, I don't think I need that extra parenthesis because I didn't start out with one. Let's divide that by 3, 4.96, and compare that again to the exact answer which we calculated way back. No, where is it? It's not showing up. All right, let's just do it again. Math 9. Math 9. Integral from 0 to 6. Sine of the square root of x dx think it was 5 something. Just over 5. So yeah, that seems a lot closer than what we got with Simpson's rule, or with trapezoid rule, I should say. So the total was 14.893 divided by 3 turns into approximately 4.964, which is pretty close. Now your calculator uses something much more sophisticated than Simpson's rule or the trapezoid rule, and they probably use a lot of different points. One other nuance about how your calculator might work things: your calculator might not work with evenly spaced intervals. It probably changes things up, so where the function is changing more, where its derivative is higher, then you're going to have smaller intervals. Where it's not changing as much, then you're going to have bigger intervals. So, okay. Comments or thoughts on that one? Clyde?
So when using Simpson's rule, does n have to equal an even value for that equation to work?
Yes. Yes. Because an even value would give you an odd number of points that contain those even interval, and that would allow you to match up that pattern that we have there. So yes, nice observation. Anything else? So you can feel fortunate that I'm not really going to cram down your throat the error terms involved in calculating some of these things. That becomes a little bit messy. So we're good.